has handouts, and those two handouts is front and back. One of them says degrees of freedom analysis, and the other one on the other side says single unit material balances. I think this is for non-reacting though. We're first going to start off with degrees of freedom. Who has heard of the term degrees of freedom before? Okay, anyone want to paraphrase it? What is a degree of freedom?
The directions the system can move.
Of sorts, more generally in a mathematical sense though. That might be for a dynamics type course. So in general, degree of freedom corresponds to how many variables that we can define. And in general, we want 0 degrees of freedom. Because if we have 0 degrees of freedom, that means every unknown in our system can be solved 100%. So we'll be talking a lot about degrees of freedom analysis, and the key thing to take away from degrees of freedom analysis is that it is much easier said than done. Right? It's almost a procedure that as soon as you know how to solve the problem, then the degrees of freedom analysis will be a lot simpler. So for someone in my position where I'm having to teach a class, I use degrees of freedom analysis to write problems because it tells me how much information I need to provide for any particular problem statement so that you guys can actually solve it. But when you're going through a problem the first time, the degrees of freedom analysis is going to feel a lot more difficult. So we'll call this NDF is equal to the degrees of freedom for a particular system. So if n is equal to 0, what that means is that the system is fully specified. And that there is a unique solution. This is what we want. We want to have the same number of equations as unknowns, and we have the degrees of freedom. So the degrees of freedom here is the number of unknowns minus the number of independent equations. And we'll talk about that too. Independent equations. So if we find ourselves in a system where we are not fully specified, we're either going to be under or over specified. So if n is greater than 1, this is under specified. And we will not have a unique solution. If n is less than 0, we have an over-specified system. And in this case, we may or may not have a solution. And we'll do the graphical representation of what each of these terms mean. That I think is really helpful. The best way, I think, to visualize over and under specification goes back to, I think, Algebra 2, when we first started to learn how to solve systems of equations. If we were to look at a 2D plot, in this case, oftentimes we call this x and y. In this case, I'm going to call it generally x1 and x2, right? These are two unknown variables. So if we have an under-specified system, we have two variables, and we need one independent equation if this is under-specified. So if I were to draw a linear equation on these axes, it would look like a straight line. This is two variables with one equation so that the number of degrees of freedom is equal to 1. For any x1 that I choose, I could very well have an infinite number of x2s. This is an under-specified system. Likewise, if we go to a system that is fully specified, see if I can squeeze 3 graphs on this table. If we have two variables, again, x1 and x2, and we have two equations, then we can have a scenario where we have two intersecting lines. And this is our unique solution of x1 and x2. Now, it is certainly possible that you could have two parallel lines, right? And then you would never have a solution. But that would invalidate this concept right here. If you have two parallel lines, then they are not independent equations. It's actually the same equation, just scaled by a constant factor. Now, there's a question, yeah.
Sorry, what did that stand for, the DO?
DOF is degrees of freedom.
Oh, okay.
Yep. Thanks. No problem. So let's push it one step over more. What if we have two variables but three equations? So in this case, we're going to say we have two variables, our x1 and our x2, and we'll have three equations. So we'll have one that potentially goes like this, one that potentially goes like this, and then maybe we have a third one that's like that. There is no solution to this problem because this one satisfies two of the three equations, this one satisfies two of the three equations, and this one satisfies two of the three equations. This is an overspecified system. Now, just because you have an overspecified system doesn't mean you'll run into this situation here where you do not have a solution. Because your third line could, in fact, go right through the true solution to the problem. And in this case, you will have a redundant equation. Right? And so what we mean by having independent equations is that you cannot transform one equation to the other by adding, subtracting, or multiplying the equations. And we'll do an example with the mass balance in a moment. The last thing that I'll talk about is that it's possible to have multiple solutions even if you have 0 degrees of freedom. And the best case of that is in a nonlinear system. So in this case here we have multiple solutions, but in this case we have 2 degrees of freedom. We could have a nonlinear equation and a linear equation. And so it is possible to have two solutions to a system of equations. Now, oftentimes, if this occurs, one of these will be a physical result and one of them will be a non-physical result. And especially common is one of these two solutions is that every variable equals 0, right? Which is, they call it the trivial solution in mathematics. Okay, this is degrees of freedom analysis, visualized. Our goal is to get to 0 degrees of freedom so we can actually come up with a unique answer, which means that everyone has the same exact solution to the problem. Okay. So that covers the first handout, degrees of freedom analysis, a little reminder. This is all the first handout here. Okay, so in the bottom half, sources of equations for non-reactive processes. This is what we're going to go through now and talk about the different types of equations. Right, in this example up here for the quiz, we just use material balances. And so far, that's basically all we've been using is material balances. But we're going to start to introduce some other more complications that make the problems a bit more difficult. Okay, so the equation sources. Now, for the most part, we have been working with material balances. So this could be the acid balance, it could be a water balance, it could be the total mass balance. And so if we were to draw out some general process, in this case it looks just like a mixer, we could have, I'll call this stream 1, stream 2, and stream 3. And for two components, I could call this m dot A1, m dot B1, m dot A2, m dot B2, m dot B3. So this is our general setup. Now we could also write this, we could also add, this is the total flow rate is m dot 1, the total flow rate here is m dot 2, and the total flow rate here is m dot 3. So we have 3 different material balance choices, exactly like the quiz example. A balance, B balance, and the total mass balance. So let me write those out, but I gotta flip this up and erase things. Didn't plan this out super well with the chalkboards. So let's just write out the A mass balance. So the A balance, it's just m dot A1 plus m dot A2 is equal to m dot A3, right? It's just in minus out. This is a steady state continuous process, which is the default assumption that we're going to make for all of our scenarios unless specified otherwise. The B balance, m dot B1 plus m dot B2 is equal to m dot B3. So let's add these 2 equations together. Right? So if I add MA1 plus MB1, what does that equal to? That's just M1. Same thing here, right? That's just M2. And this is equal to M3. And this is the total balance. So if I add the A species balance plus the B species balance, I get out the total material balance. So I only have 2 independent equations because the third equation is just a combination of the other 2. So for material balances, you get 2 independent equations per species. But you can choose any 2 of these 3. Because if I were to take the A balance and subtract, if I were to subtract the A balance from the total balance, I would get out the B balance. Right, so sometimes it makes sense to do the A and B, sometimes it makes sense to do the A and the total, and vice versa. But the key thing to keep in mind is that when you're doing your degrees of freedom, you get to generate 2 equations for every species in the system. And I believe it says that right there in your checklist of things. Okay. Now, so this is a really simple linear combination to show that this is a dependent equation, but you can have, for example, like 2 times this equation minus 7 times this equation, and that gives you this one here, right? So you can have a lot more complexity when it comes to dependent equations. Okay, the next source of equations. When we start talking about energy balances, you will get 1 additional equation. That's because there's only basically 1 energy to worry about. There's not like multiple different types of energy that we're going to be worrying about. It's just the total amount of energy is conserved in the process. So when we get to energy balances, that will add 1 additional equation. Now, where will we be spending most of our time is in the next category, process specifications. Well, for now, and then later on we'll be doing a bit more. So the next source of equations is process specifications. These are going to be details regarding the specific problem that we're going to be working on. What is the concentration of a stream? What is the ratio of 2 different streams being flowed together, right? So for example, air has a process specification of being 21% oxygen and 79% nitrogen. So that is a process specification of air. Now, one thing that's really important to note here with air is that if there's no reactions occurring, the oxygen and nitrogen material balances are not independent, right? They're dependent on one another. Because I can get to the flow rate of oxygen as equal to 21 over 79 times by the flow rate of nitrogen. right? So unless there's a reaction occurring, like where some of the oxygen is being consumed in a combustion process, these are not independent reactions. But the process specifications, these are going to encompass most all of the interesting aspects of the problems, right? We're going to say, oh, 10% of stream 1 goes to stream 4, or the ratio of stream 7 and 8 is 2 to 1, right? These are going to be different process specifications.
I have a quick question.
Yes?
Kind of going back to that first one, you have 2 independent equations per species.
Yes.
But to the left, I'm seeing you have the A species and B species.
Mm-hmm.
So should we have 4 equations?
So the independent species in this system is you have material of type A and material of type B. And the key thing here is that we can tell the difference between A and B. So A could be ethanol and B could be water, or A could be acid and B could be water, for example. And so the idea here is that since we can tell A and B apart, we can do an independent balance on each of those 2 species. And then you always, of course, have the total balance itself. So how are you getting to 4 in this
You
example?
have 2 independent equations per species is what you had said, but is it supposed to be 1?
Oh, you get 1 independent equation per
Okay,
species.
that's-
Yeah, that is the better way to put it. So yeah, you get 1 independent equation per species. Sorry, I said that was I wrote that down incorrectly. Okay, thank you for that clarification. The next source of equation is going to be physical properties. Right, and this is going to be something like vapor pressure, density, vapor-liquid equilibrium, VLE is what I often write that as. That's basically relating between the composition of a liquid stream to its composition in the vapor stream. This could be an equation of state, like the ideal gas law or the Peng-Robinson equation of state. Right, so ultimately, as we're marching down in the class, I'm going to be giving you less and less arbitrary specifications, and we're going to rely more and more on real thermodynamic processes. Right, so let's say, for example, I have a glass of water that's half full, and I put a lid on it. Eventually, some of that water is going to be evaporating into the vapor space, the gas space. At the start of the class, I'll say 3% water in the gas phase. But as we march on in the class, I'm going to say, I want you to calculate how much water is in the gas phase, and then use that information to balance the material process out. Right, so that's an example here of vapor-liquid equilibrium, or a distillation column, or a flash separator, or a crystallizer. So we're going to be starting to introduce more and more fundamental thermodynamics as a way to alleviate having to give you a cookie-cutter process problem to solve. And then lastly, the last source of equations is physical constraints. So another way to think about this is kind of like mathematical definitions. So for example, the summation of all of the mass fractions has to be equal to 1, or the summation of all of the mole fractions have to equal 1. Right, this is just something that is based on the definition of the terms that we're talking about. So these are our sources of equations. Are there any questions? And then we'll start to do an example where we walk through the process of doing degrees of freedom analysis, writing down all of our equations, and classifying them into one of these categories. Now, the way that I'm going to do this example is I'm going to do it sort of in like a dummy way, where I'm just going to write out all of the variables. And I'm going to make it as arbitrarily complex as I can, just to show that the degrees of freedom analysis works. But you'll want to be making certain approximations along the way as you practice these problems more. So what we're going to be dealing with is a distillation column. Where entering it, we have 1,000 kilograms per second of a 10% ethanol and 90% water solution. So I'm going to simplify this down really quickly right now and just write out 100 kilograms per second of ethanol and 900 kilograms per second of water. Coming out of the top stream, 10% of the feed goes to the top or the what we call the distillate. What kind of a piece of information is this?
Process specification.
It's a process specification. So how do we take this process specification and convert it into an equation with variables that we can count in our degrees of freedom?
Multiply by mass squared.
So can someone tell me an equation that I could write?
100 kilograms per second is what would be coming out, or the flow would be right there, right?
Right, so you've done the math already,
Okay,
but can we simplify that down to the actual equation? So what I would say is that m dot d is equal to 1 over 10 m dot f. 1/10 of the flow rate of the feed goes to the distillate. This is what's going to be the difficult part in the class, is translating these process specifications to an equation that we can literally solve, right? Because for this one it's simple, but they're going to get more and more complex. And you're going to have to substitute this equation into something that you don't have, for example, and it's going to get a bit more difficult. The other specification that we have here is that the top stream is 60% ethanol and 40% water. Again, that's another design specification. So the unknowns that we have in this equation still are m dot E in the distillate and m dot water in the distillate. Now we know nothing about the bottom stream. So we don't know the total flow rate of the bottom stream. We don't know its composition. So let me write this things. We don't know the composition, so we don't know X of the bottom for ethanol, X for the bottom for water, and we don't know the total flow rates, the mass of the bottom of ethanol and the mass of the bottom for water. Now I understand that some of these we can do the approximations right away, but what I'm just trying to demonstrate here is that we can use all of the different types of equations to simplify what we're working on. Okay, so if I did this right, we should have a total of 8 unknowns. 1, 2, 3, 4, 5, 6, 7, 8 unknowns. So we need to find 8 different equations. So where can we get some equations from?
We know that the flow rate at the bottom, what's the, not distillate, but what's the bottom supposed to be called?
This is the bottom stream, yeah, B, bottom. So,
Okay, so that's going to be 9/10 of 10 that. The flow rate of that should be.
yes, that's one strategy. Now, what you've done there is a total mass balance in your head. So let's go through and let's do it list by list. So the first one that we had is what I erased here, is on your sheet for the sources of equations, material balances. So how many material balances do we have? How many independent material balances do we have in this system here? 2. 1 for water, 1 for ethanol. 1 per species. Okay, so energy balances, we don't have any of those. So process specifications. This one's a bit trickier. I find 5 process specifications. Well, yeah, see, I kind of classified these ones weird. I think there's really more like 3 process specifications and then, yeah, so 3 process specifications is what I find. So we've got 1 here. The mass of the distillate is 1/10 the mass of the feed. We have another one here, 60% ethanol and 40% water. That gives us 3 equations. 4 physical properties. We don't have to worry about any of that because everything is already in terms of the mass flow rates. And then 5 physical constraints. So 2 of these you could kind of say are design specs, and 2 you could maybe say are physical constraints. I count 3 here. So we've got 1